If you're trying to understand extremely tiny things, things that are smaller than atoms, the physics that comes into play is called quantum mechanics. If you're looking at a huge mass, the physics that comes to play then is called general relativity theory. If you're looking how the universe behaves at extreme speed, then it's special relativity theory. So speed is the fundamental core of special relativity theory. But what is speed? In everyday life, speed is nothing but distance divided by time. For example, if a car reaches a 100-kilometer distance in 1 hour, we can say that the car speed is 100 kilometers per hour. It looks simple, but speed has unusual features when it gets into very high numbers, especially its unusual effect on space and time. Speed is relative. It can vary one to another. This means that different frames of reference will get different speeds of the same moving object. But the speed of light is not like that. It travels at a constant speed, which means that the speed of light is the same for all observers, no matter the observer in motion. But why is the speed of light constant? Why is it always 300,000 kilometers per second? How did scientists figure out the speed of light? What is the great discovery Einstein uncovered with the help of knowing the exceptional feature of light? Why can't anything travel faster than light? Let's see. As a matter of effect, the study of light doesn't just arise during Maxwell and Einstein's time. The debate has been going on for about 2,300 years. As far back as the times of ancient Greece, the philosopher Aristotle said that light has no speed, that light was instantaneous. This claim lasted for more than 1,500 years, because measuring the speed of light is not trivial. Finding the speed of light is not as easy as finding the distance a man walks. Light travels so fast that there was no way to detect its speed at the time. In the 1600s, the famous scientist Galileo believed that light had a definite speed. He not only believed, but also tried to measure that speed. He and his assistant each took a shuttered lantern, and they stood on hilltops 1 mile apart. Galileo flashed his lantern, and the assistant was supposed to open his lantern shutter as soon as he saw Galileo's light. He tried to calculate how long it would take the light from his lantern to reach the assistant on another hilltop, but he could not. The reason is that a mile is too short a distance to calculate the speed of light. In fact, knowing the speed of light now, for light to reach 1 mile away, would take 0.000005 seconds, far too fast for human reflexes. Then in 1670, the Danish astronomer Ole Romer was studying the orbital path of Jupiter's moon, Io. After studying its motion for 2 years, he found something strange. Io takes 1.77 days to orbit once around Jupiter. The time it takes to make each orbit is always the same. But he discovered that the moon didn't always appear where it was supposed to be. At certain times of the year, it seemed to be slightly behind schedule. At other times, it was slightly ahead. Romer wondered why it would orbit more quickly sometimes and more slower at other times. Finally, he noticed that Io seemed to be ahead of its predicted orbit when the Earth was closer to Jupiter, and behind when it was further away. Perhaps if the speed of light were infinite, then Io would be visible to us on Earth at the same time its orbit. However, he found that the light from Io takes a few minutes to reach Earth, so light has a certain speed. He also found the speed of light using the locations of Earth and Jupiter, so he calculated the speed to be around 200,000 kilometers per second. Following this, in 1728, James Bradley, an English astronomer, found that Jupiter's distance was not far enough to calculate the speed of light, so he spent time observing a distant star. Observing this star, he found that its apparent position changed throughout the year. He calculated the speed of light to be 301,000 kilometers per second by investigating it through a stellar apparent method. It wasn't exactly the speed of light, but it was close. Although subsequent experiments were carried out by other scientists, an experiment in 1887 became the most famous. Sound needs a medium to travel through, such as air. Ocean waves are relative to the water. Similarly, Michelson and Marley conducted an experiment to prove that light needs a medium to travel. The experiment was conducted to prove that a substance called ether pervades the universe and acts as a medium for light. This experiment ended in failure, and it became clear that light does not need any medium to travel. It can travel through both medium and vacuum. The Nobel Prize was awarded for this discovery. At the end of their failed experiment, they calculated light speed to be 299,910 kilometers per second. This value was believed and remained in use for scientific calculations for some years. Then at a turning point in the history of science, the speed of light was precisely calculated with mathematical equations by Scottish mathematician and scientist Maxwell. He was just thinking differently. Electromagnetic waves always travel at the same speed, no matter if they are longer or shorter waves. They always travel at a constant speed. With his equations, he found the speed of electromagnetic waves and velocity of light are exactly the same numbers, 300,000 kilometers per second. So he finally concluded that if the speed of electromagnetic disturbances is equal to the speed of light, then light itself must be an electromagnetic wave. Now, it's clear that light is an electromagnetic wave which travels at a constant velocity. But what is constant? Imagine a car X traveling at the speed of 20 kilometers per hour. A stationary person near the roadside now measures the car's speed, and he measures the value at exactly 20 kilometers per hour. Now a car called Y comes from the opposite direction at the speed of 20 kilometers per hour. A person from car Y measures the speed of car X, and it shows 40 kilometers per hour. Velocity of car X plus velocity of car Y is equal to 40 kilometers per hour. Now take another car called car Z, which is moving away from car X at the speed of 10 kilometers per hour. If you measure the speed of car X from car Z, you will get the speed of car X as 10 kilometers per hour, because 20 kilometers per hour minus 10 kilometers per hour is equal to 10 kilometers per hour. How can the speed of the same moving object give different rates of speed for different observers? There's no need to wonder because speed is relative. But if you measure the speed of light, no matter how fast you move away from the light, or no matter how fast you move toward the light, it always shows the same speed, 300,000 kilometers per second. Let's put an example of you traveling on a bike at the speed of 10% of our speed of light, which is 30,000 kilometers per second. So the speed of light from your bike doesn't equal 330,000 kilometers per second. It remains 300,000 kilometers per second always. The speed of light is constant and doesn't depend on the speed of light source, but there is no explanation for why the value is constant. It's a fundamental law of nature. So, to maintain the constant velocity feature, space and time experience unusual features such as time dilation and length contraction. So in this universe, everything is relative except the speed of light. With the core idea of constant velocity of light, Einstein developed his special relative theory, which gave us a new way of understanding the nature of time. We already know only light itself can travel at maximum speed in our universe. Can anything travel faster than the speed of light? To get the answer for this, let's take a look at a relativistic mass equation. Relativistic mass is equal to rest mass divided by root of 1 minus v squared by c squared. Relativistic mass is nothing but how much mass increased when the object is in motion. Here, rest mass means original mass of an object. V means velocity of the motion object. C means velocity of the light. If an object moves 10% of the speed of light, for example, its mass will only be 0.5% more than normal. But if it moves 90% of the speed of light, its mass will double as an object approaches the speed of light. Its mass rises precipitously, and once it tries to reach the speed of light, its mass becomes infinite. If we look at Einstein's mass-energy equivalence equation with this infinite mass, the energy required to move this object also becomes infinite. Even our universe itself has finite energy. How can we get infinite energy to move the object? So this is the reason that any massed thing in this universe can't travel the speed of light. As we saw earlier, to maintain the constant nature of speed of light, time acts weirdly, and the end of the result causes time dilation. Einstein is the only man who discovered this feature of the universe, and he described this in his special relativity theory. Does this mean his theory tells us that time really slows down at an extreme speed? If it's true, light itself actually doesn't feel any time. Let's see these details in another video soon.